So today we have Yossi giving an introduction to topological data analysis.
Yeah, hi. Thanks, Sarah, for inviting me and arranging a time that is not like 1 in the morning for me to be able to give this. So today I will try and discuss what donuts tell us about data as a way of introducing topological data analysis. I have written this talk for a very low level of assumed background knowledge. So this should be accessible to anyone that has kind of done some standard Australian second or third year maths classes. I'm trying to keep an eye on the chat / the participants. So if you have any questions, feel free to just interrupt me. I welcome addressing questions partway through. And yeah, so thank you very much again, Sarah. All right. I'll start by giving a brief description of the main tools in topological data analysis. And they are quite conveniently variations on a single theme, which is just homology with various brackets of co at the front, depending on which way you want your arrows to go. And depending on the type of data, typical variations are persistent homology and persistence diagrams, which I'll be focusing on this particular seminar, homology of complexes, or homology of thickenings. And by thickening in this case, I mean, you just have some data or space embedded in some Rn, and you look at a sublevel set of the distance function to this subspace or subset. So, given a topological space, the homology groups just record linear combinations of closed I manifolds within X. And I'm guessing that we're all pretty much topologists, so we all have that same disappointing moment in the morning where you find that your coffee cup does not, in fact, taste like a donut, and that your donut is not a great beaker to hold coffee in. I spend my life cleaning up after such mistakes. And so this is kind of a very basic and foundational notion in TDA, is you end up wanting to kind of count persistent features. All right, so what's the TDA pipeline? A very good example, with many thanks to Michael Kerber, who I stole these pictures off through my supervisor. We can visualize the TDA pipeline as such. We have some input points at the top. We then do some magic, and in this case, look at the homology as we thicken the point clouds and take their union, and then we have some conclusion. And quite often, this conclusion is visualized, or we look at it through the use of persistence diagrams, which I'll describe in a bit. So we'll start with a very, very, very basic example. This is where I'm not quite used to doing things online, because normally there is a lot of audience participation. Does anyone know what this game is? Feel free to just shout it out. All right. It's a game called Carcassonne. And you have these little tiles, and the tiles have some combination of a castle, fields, and roads on them. And what the aim of the game is, you play these tiles one by one and you collect points. And at the end, there is something to do with how the fields and their connected components scores points. So for this example, we're going to play a game of Carcassonne and try and track how the connected components of the fields change. Sounds like my cup of tea at 8 in the morning. It's like 6 in the US, right? It's great. Great time to play a game. So you start with one piece, which has always got 2 connected components. And then as you place the next piece, you're able to go around the abbey and have now connected those 2. So we've lost one of these connected components. As we play the next piece and play it down the bottom here, One of the connected components, nothing really changes. We've just enlarged it a bit, but we get two new ones. And as we continue, you can see that there's some combination of things that happen. Either we kind of just play a place and nothing interesting happens, or some connected components merge, or some are, introduced. Many thanks to my supervisor, Kate Turner, and her now master's student, Kelly, for doing this one. Getting one of these examples is a tedious task, having done one myself. So as we keep going, we end up with this final one. And so this is the final state of the space we're looking at. We've got 1, 2, 3, 4, 5, 6, 7, 8 connected components. But really, it's quite interesting to look at what's happened as we've played this game. So let's introduce language about how we do this. As the parameter changes in this particular example, as we place one card with each step, a few things can happen. Either nothing happens, we've just kind of increased the amount of space one of the connected components takes up. New elements can be introduced, so they are born in the language of persistent homology, or elements can disappear. So when two connected components merge, we say something has died. I know it's really morbid, and doing this at 8 in the morning is a great way to start my weekend. So we say an element A in a homology group is born at R if it first appears in the homology group when we take the XR filtration step. So in this case, the orange one that was on the third tile was born at time step 3 because that's when we introduced it. And it dies at R if it is in some X, the homology of X for R prime, but not for R, for some R prime in an interval with supremum R. This is really complicated, but essentially you see it and then suddenly you don't. And working with supremums is because quite often you deal with the parameters being the real 9, and so you don't have discrete time steps to just talk about distinct things. All right, now that I've spoken a lot about things being born and things dying, and we're on a really great morbid subject, how do we track this? Well, birth and death certificates may be too morbid, so one way is to use a barcode. And it's just a set of bars for each homology dimension, where a bar represents a persistent homology feature. A bar begins where that feature is born, and it ends where it dies. So looking at this previous example, we had, actually this is for an example you are yet to see. So I will go through and we are going to see how this barcode evolves with a different example. Can everyone kind of see the colors on this new example in the top right? I'm hoping that because it's on your laptops, it's all good. If you get confused with any of this, feel free to shout out and let me know. So this time, rather than the filtration being, I'm going to play one card at a time, we're starting at time step 0, where we have samples where we know what's on 3 separate cards. And as we go through this example, we're going to be looking at not just these individual cards, but we're going to go one card step out and look at all of the 9 neighboring cards. And then we're going to look at the neighboring cards of that again until we've covered this little black square. So at this time step 0, we've got 1, 2, 3, 4, 5 connected components, and we've got 1, 2, 3, 4, 5 bars, which are conveniently color-coded. When we now look at the next step out, you can see that one of the bars has died because 2 connected components merged, and a whole heap more have been introduced. When we do this again, you can see that, again, some things have died and some things have been born. And when we finally get this, we can track the persistent homology of looking at expanding kind of snapshots of this particular game and track it using a barcode. Everyone following me this far? I know it's late for you, early for me. All right, we good? All right, barcodes are great, but in some ways, right, like if you've got a long persistence like filtration with lots of time steps, it's kind of inconvenient to be carrying around these infinite bars. Right? You need an infinite backpack to count your infinite bars, and that's a big backpack. And I don't think I can carry that. So let's try and come up with some other way of tracking it. A different way of tracking birth and death is to use a persistence diagram. A persistence diagram is just a multi-set of points in the plane where you have infinitely many copies of each point in the diagonal, y equals x, and birth-death pairs for each persistence feature counting multiplicity. Now, one thing that I will point out is that points that are kind of represented like right atop the cross at the top, these have got infinite death values. So they represent the infinite persistence features, and the number next to them is just the multiplicity. Whereas in the barcode, you could see, oh, we've got 4 bars that have got this same length. When you're plotting these in a plane, if you plot 5 points on the same place, it's kind of hard to tell you've got 5. And so we use these multiplicities to keep track of that. Now, you can move from a persistence diagram to a barcode uniquely, so you don't lose any information going between them. And I will preempt a question I will get now and say that there are infinitely many copies of each point on the diagonal so that we can compare persistence diagrams. Given we're working with a multi-set of points, the way of kind of comparing persistence diagrams is to look at matchings between them and the cost of such a matching. And so if we've got persistence diagrams with a different number of points, you can't necessarily construct a matching. And so you can just easily throw in infinite points along the diagonal because this does nothing to the matching. Every point on the diagonal gets matched to itself in the other diagram, so associates cost 0. And then any of the finite other points you can just match as best appropriate. All right, data and homology inference. All right. We want to understand the shape of a space X embedded in some Rn. Now, I don't know about everybody else, but my computer is not very great if I give it a circle and tell it to remember that a circle is in fact continuous. So we're going to assume that we only have points sampled from the space X. We want to understand or guess what's the shape of X. A really good first guess is to just pick your favorite radius r bigger than 0 and attach a ball of radius r at each point and be like, X is the union of these balls, and I'm sticking with it. That's it. I'm committed. I don't care. We're all good. All right. This is the part where I, again, have lots of audience interaction where I ask them if this is an appropriate choice of r to attach to each of these balls. I guess we've got the raise hands feature, or yes, no. Do people think that this is a great choice of radius for these points? No? A very, very vocal no that suddenly came out of my computer. All right. What about this one? Strong thoughts, opinions, feelings?
It's aight.
It's aight. That's a bit rough. All right. This one, feeling a bit better? All right. Surely we're getting kind of close. All right. Who agrees that this, given we have now recognized a circle, is probably the optimum choice of ball to pick? Yeah? All right. I mean, I like this one, but personally, this one is my favorite because the best space is clearly just Rn. Just let the radius of the ball be infinite, and then you always have whatever your embedding space is, nothing to analyze, pure and simple, job done, go home. I can go back to bed. All right, so yeah, there's kind of consensus that this one or this one, probably this one would be the best size radius to use. But you don't know that at the start, right? So, right, how can we do this? Well, you know, addressed important questions. What's an appropriate radius? And I was hinting at this earlier. We can look at what happens as the radius increases. And so studying the changes in homology as this parameter increases leads to the notion of persistent homology. So we are looking at changes in H0, H1, and potentially H2, where we are looking at each of these as we increase. And many thanks to, again, Cheyenne Mukherjee, who I stole this off through my supervisor, Kate, for the images. All right. So, persistent homology. It's applicable whenever we have a sequence of spaces nested by inclusion. There are variants where you can have zigzag inclusions. So you can have a sequence of spaces where you include one space into spaces left and right, and then these ones get included into from the other side, so you can go up and down. But standard persistent homology is just you have a flag of spaces, inclusions all the way up. Any questions, comments, thoughts before I move on to discussing some applications and then end up with some code demonstration?
Do you know, maybe you'll talk about this in applications, but do you know any examples of such increasing filtrations of spaces that don't come from periodic data sets?
That don't come from periodic data sets?
Yeah.
Yeah, a whole heap. I mean, if you sample GPS locations of cars on a city or like on roads at any particular point in time, and you want to understand the road network that's not periodic. Okay, cool. You can look at, there's a whole heap of applications, including, an example I'll talk about in a little bit is you can use persistent homology to look at shapes of bones of monkeys and things like that. So a few people have done that. There are a bunch of biologists that use it or are trying to use it to distinguish between certain things, which hopefully will work. I'm trying to get the code to run and we'll hopefully have results soon. All right. Any other questions?
Thanks.
All right. So an application that I learned right at the start, which I personally think is super cool, is that TDA was used to identify subgroups of type 2 diabetes by looking at patient similarity and then identifying that you kind of have 3 distinct clusters and a 1 cycle. So from memory, I haven't looked at this paper in a while. What they did is each point represents either a single or a group of patients. And if it's a group of patients, then the individuals in this group have got clinically significant similarities in a significant number of clinical markers and observations. And so for all intents and purposes, we can merge them. And then edges, as it says here, connect nodes, indicate that the nodes share patients. Red colors are enrichment for patients with T2 diagnosis, and blue is non-diagnosis. And they use this to identify 3 subtypes of type 2 diabetes, which I personally think is super, super cool. All right. Moving away from medical stuff, now to things which are closer to home for me and are highly related to my PhD project. I'm going to talk briefly about moving towards stratification learning through homology inference. So Paul Bendick, Beiwang, and Cheyenne Mukherjee have a couple of years ago used persistent homology to determine whether 2 points in a sample of a stratified space have come from the same strata or not, or look like they're in the same strata. And so the idea is that if you have access to the entire stratified space and you pick 2 points and you look at a thickening, if they come from the same strata, their persistence diagrams should be roughly the same. And in fact, you can do kernel and co-kernel persistence of the diagrams, which sounds a lot harder and more difficult than it is. It's pretty simple. You just look at the co-kernel of the maps and the map kernel of the maps when you go from this circle into the union, into the intersection, and from this circle into the intersection. And then now when you do this with a point cloud sample, you should have nothing in this kind of region around this top empty area if they have come from the same strata. Because it's a noisy sample, we expect there to be some room, and we expect a lot of changes, in particular in H0 for this case, because we start with a discrete point cloud sample and are then thickening. So there'll be lots of little changes at the scale down here in the bottom left. And then as it increases, nothing really should change until much later. That should be kind of one persistent feature much later. All right, so that's an example where they come from the same strata, and now where they come from different strata. You can, this pink region is not empty because there is something that changes when you map from one ball into the inclusion versus from the other ball into the inclusion. There's a difference. And we can expect to see that because if we look at the persistence diagram of just the stratified space and look at these, there is a point here which is born and then dies. And it's not, doesn't persist. So we'd expect, given a data point, given a noisy sample, some points in this kind of shaded pink region. Happy with that example? All right, now here is something that is much more hands-on, and I will hopefully demonstrate in person. So, persistent homology of simple closed curves. This you can do for nice closed spaces in Rn, but for diagrammatic reasons, and because I do not want to break my brain, we're going to stick to closed simple curves in R2. So given some curve C in R2, simple and closed, we can create a sequence of spaces connected by inclusions by considering a sublevel set of a height function in a specific direction U. Right? Seems reasonable. We've picked some direction here and then gone up and across. I will warn you that this persistence diagram was generated with a slight bug in the code. So this point up at the top left should actually die at some point. There was, yeah, that bug's been fixed, but unfortunately I forgot until just now that this was generated before that. So as we start and sweep up, there's kind of, we hit a point and then this will persist forever. And then as we go up, there's all of these tiny little bumps that happen near the diagonal. I will note that earlier when I was showing persistence diagrams, they all lived in the upper right quadrant of R2. Given closed curves in R2, that doesn't always make sense because if you want to take height functions in specific directions, then where that curve is located in R2 kind of changes everything. So what we've done is we normalize the images by placing kind of the centroid of the curve at the origin. And so you can have points with negative heights. So things are born with negative heights, but there is a very unique way to move from like this to it just being centered in the origin. All right. Here is a different simple closed curve in R2. Again, same thing, weird point. I feel really bad because I'm the one that wrote the code, so I can only blame myself. Now, all right, chose this particular direction. What if I'd chosen this direction? Is there any consensus as to which is a better direction for describing the shape of this simple closed curve? Who thinks direction 1 gives us a better example? And who thinks direction 2 gives us a better example? Someone pick one.
I'd say direction 1.
Direction 1? You think this one gives us a better example? All right, throw a spanner in the works. What if I now say this is also a direction? Which one?
I like this one better.
You like this one better? Yeah, I mean, there are virtues to all three of the directions, and I have some more examples that I can show you as to how, when you look at different closed curves, you get different summaries of what looks, right? Like in this curve, sweeping down from the top right to the bottom left, there's lots of activity the whole way along, right? Lots of tiny little bumps. But when we pick this other direction, we see almost none of them. And here's a different example. Again, depending on the direction, we either see things in the bottom left quadrant of the persistence diagram or the top right, or we see lots of things all over the place. So which direction should we choose? We had this radius issue of how we do it, but now we kind of can't do that because we've got a parameter, which is, you know, the height along an angle. What should we do? Do we just choose a particular direction? Do we
I'm a
choose
little
a
bit
set of
confused on
directions?
what you're doing with the directions, because I thought that the persistence diagram that you were showing, I thought that that was the recurrence plot.
So this is, so you take the height function in this direction, and then you look at, for each value, your filtration is then just sub-level sets. So you look at everything that is, in this case, to the left of a specific horizontal.
So corresponding to a direction, you have a height function.
Yeah.
Okay, got it.
And then how do you pick which direction you take this height function in and go from there? Well, thanks to Turner, Mukherjee, Kate Turner, my supervisor, Cheyenne Mukherjee again, and Doug Boyer, we can take all the directions simultaneously. So in this particular instance, we have S1 directions. Again, my computer loves me because it loves to think that a circle is a discrete object. So every time I tell it, no, 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 there's another one, it's like, no, you are crazy. This is the maximum number of points I can have on a circle, and that's it. So they introduced what they called the persistent homology transform. I personally think Kate should have come up with a much cooler name, but you know, it's a bit late now. And for now, we will denote the space of persistence diagrams by just PD. And when I write PD to the D, I just mean we've got D copies of it, one for each homology dimension that we're interested in. In particular, I will point out that given you are looking at a subset M of RD, you can have, and it's like nice and well behaved, you have nothing interesting happening in the Dth dimension, right? So we've got 0 to D minus 1. So given a subset M of RD, the persistent homology transform of M is the map PHT of M, which goes from the S D minus 1 sphere to D copies of persistence diagrams, where it maps a direction, which we can either think of a unit length vector or a point in this sphere, and takes it to the persistence diagrams in each homology dimension using the height function in this direction. With me so far? I see 3 faces that are not mine, and I'm just taking that as a representative sample. 3 seems somewhat appropriate given the number of participants. 1 and 7, that's fine. The statisticians I work with are going to kill me. All right. I had added some other stuff, but now is the time for demonstrations of code. Let me get this up. Sorry. Do you mind if we stop the recording for now?